Your SSD has an expiration date, not a sticker on the box, not a warning on the packaging. A real one, ticking down right now, invisibly, inside the machine you're using this second. And almost nobody who owns one has ever checked it. Every photo you've saved, every project file, every tax document sitting quietly on that drive is riding on a piece of memory that was never designed to last forever. It was designed to wear out. That's not a flaw, that's the spec sheet. And the strange part is, this has already happened before, more than once, to more than one kind of storage, and every time people were caught completely off guard. If you're new to Nolan Tech, make sure to subscribe and turn on notifications because we upload new tech videos regularly that help you stay ahead. Here's the thing that most people never think about. Every storage technology we've ever trusted has gone through the exact same life cycle. It doesn't matter if you're talking about magnetic tape from the 70s, floppy disks, spinning hard drives, or the solid-state drive sitting in your laptop right now. They all follow a strangely predictable arc. And once you know what that arc looks like, you start noticing exactly where your own drive sits on it. It starts with a honeymoon phase. A new storage format shows up, promising to fix everything wrong with the last one. Faster, more reliable, more efficient. Early buyers jump in, reviewers rave about it, and for a while, it genuinely performs. That's not marketing spin. The tech usually does work well out of the gate. Confidence builds. Nobody's asking hard questions yet because there's no reason to. Then adoption explodes, prices drop, the technology shows up everywhere, and usage patterns change in ways nobody originally planned for. Software gets rewritten to lean harder on the new hardware. People push it further than the engineers who built it ever expected. And underneath all that growth, wear starts accumulating quietly, invisible, because on the surface, everything still looks fine. Eventually, the wear catches up. Failures start showing up, but not randomly. They cluster around specific models, specific manufacturing batches, specific usage patterns. At first, it looks like bad luck. A forum post here, a returned unit there, then the pattern becomes too consistent to ignore, and by the time it's undeniable, a lot of people have already lost something they can't get back. That's the cycle. Foundation, expansion, crisis, reckoning. And the unsettling part is that every generation of storage tech has walked through all four stages almost exactly the same way, including, right now, the SSD in your computer. Let's rewind to see it happen for real, because this isn't a theory. It's documented history, and the paper trail is long. Go back to 2008. Seagate released a line of hard drives that, on paper, looked like a huge leap forward. Solid capacity for the time, fast spindle speeds, aggressive pricing that undercut the competition. Reviewers loved them. Businesses bought them by the pallet. For months, everything was fine. Then, without warning, drives started bricking themselves. Not slowing down, not throwing errors first, just gone. The computer wouldn't even recognize that a drive existed anymore. It turned out to be a firmware bug, not a mechanical one. Under a specific combination of conditions, the drive's own controller would corrupt its internal firmware and lock the whole device into a state nobody could access. Not the user, not the BIOS, not even specialized recovery tools in a lot of cases. Seagate's first instinct was to blame users. Bad shutdowns, unstable power, anything other than a design flaw. But the reports kept multiplying. Data centers started seeing entire racks of drives fail in the same week. And eventually, the company had no choice but to admit there was a real problem and start pushing firmware fixes. Here's the cruelest detail. The fix only worked on drives that were still alive. If yours had already locked up, there was nothing left to patch. Your only option was an expensive, invasive data recovery process that didn't always work. Estimates put the number of affected drives well over 1 million, and the resulting lawsuits and settlements cost the company for years afterward. New safeguards eventually got built into later designs, and the industry moved on the way it always does, promising the next generation would be different. Now, you might be thinking that's a hard drive problem, moving parts, spinning platters, mechanical failure points that solid-state storage was specifically built to avoid. Fair point. So let's look at something with 0 moving parts that failed in almost the exact same shape. Rewind further to the late 90s. A batch of Taiwanese manufacturers got their hands on what they believed was a proprietary Japanese formula for long-life electrolytic capacitors, the tiny components on nearly every motherboard, graphics card, and power supply that regulate voltage. The problem was that the formula they copied was missing a key stabilizing ingredient. They didn't know it. They mass-produced these capacitors anyway, and for roughly a year nothing looked wrong. Voltage regulation was normal, products shipped, customers bought them. The flaw was chemical, and chemical processes take time to show up. Then, right on schedule, capacitors started physically bulging and leaking electrolyte, usually somewhere between 18 months and 2 years after manufacture, almost like a countdown. Motherboards died, power supplies failed. Photos of the telltale dome-shaped, swollen capacitor tops spread across enthusiast forums years before mainstream tech coverage caught up. By the mid-2000s, estimates of affected motherboards ran into the millions, spanning products from nearly every major computer brand. And the financial fallout stretched into the hundreds of millions of dollars, all traced back to a stolen recipe with one missing ingredient. Still not convinced? One more example, and this one is solid state, no moving parts, no capacitors, just flash memory. In the early 2000s, flash memory cards took over digital cameras, MP3 players, and the first generation of smartphones. The pitch was simple. No moving parts, reliable long-term storage, ratings that promised roughly a decade of data retention and well over 100,000 write cycles per cell. People trusted that math completely. Prices dropped, capacities climbed, and manufacturers leaned into cheaper manufacturing processes and denser cell designs to keep up with demand, which quietly traded away some of that original endurance margin. Then people started noticing something strange. A photo would look perfectly fine on the camera's screen, but transfer cleanly corrupted files to a computer. A saved video would play fine one week and refuse to open the next. This wasn't dramatic, obvious failure. It was quiet data rot, cells slowly losing their ability to hold a charge, sometimes years earlier than the advertised lifespan. Most people blamed themselves, assuming they'd done something wrong rather than recognizing a storage medium quietly failing underneath them. Data recovery specialists eventually documented the pattern clearly. Real-world endurance was falling well short of the marketing claims, especially in warmer environments where charge loss accelerates. 3 completely different technologies, 3 completely different failure mechanisms, firmware, chemistry, charge leakage, and yet every single one followed the same 4-stage arc, almost beat for beat. So where does that leave the SSD sitting in your own machine right now? If you're enjoying this video and finding it useful, take a second to like the video and subscribe to Nolan Tech. It really helps the channel and lets us keep making detailed tech content like this. SSDs had their honeymoon phase in the late 2000s and early 2010s. No moving parts, near instant load times, silence, shock resistance. A genuine, well-earned upgrade over spinning drives. Early endurance ratings looked almost absurdly generous for normal use, and people quickly came to trust that SSDs had simply solved the reliability problem that hard drives never could. Then came the expansion phase, and it's still going on. Prices per gigabyte collapsed. Capacities exploded from a few hundred gigabytes to multiple terabytes, even in consumer laptops. Data centers shifted entire storage arrays to flash, and along the way, the underlying memory technology quietly changed to keep costs falling. Early drives used single-level cell NAND, where each memory cell stores 1 bit. Extremely durable, extremely expensive to scale. To hit consumer price points, manufacturers moved to multi-level cell, then triple-level, and now quad-level cell, NAND, packing more bits into every physical cell. Each jump made drives cheaper and bigger, and each jump also cut the number of program erase cycles those cells could survive, from around 100,000 cycles on the earliest SLC chips down to roughly 1,000 cycles on today's densest QLC chips. Smarter controllers, larger reserved spare areas, and better error correction have done an impressive job hiding that trade-off from the average user. But the underlying physics didn't get more forgiving. It got tighter, and the software just got better at managing it. Meanwhile, the way we use drives changed too. Background sync services, automatic cloud backups, huge game patches, constant OS updates, security scanning, all of it writes data continuously, mostly without you ever noticing. None of this shows up as a warning. Health percentages in monitoring tools sit comfortably in the high 90s for most of a drive's life, right up until they don't. And that brings us to where things actually stand today. We're sitting somewhere between the expansion phase and the early edge of the crisis phase. Not universal failure, nothing close to panic-worthy for most users, but enough documented failure clusters that the pattern is visible if you're paying attention. A few real examples make this concrete rather than abstract. Certain Samsung consumer drives using early TLC and AMD showed measurable read performance degradation on older, infrequently accessed files, a known characteristic of charge leakage in worn cells, addressed over time through firmware and controller improvements. A batch of Intel Enterprise SSDs years ago hit a specific firmware bug tied to an exact power on hour threshold that caused affected drives to suddenly report almost no usable capacity. Intel patched it. But any drive that hit the bug before updating lost its data outright. Early SandForce controller drives from a now-defunct manufacturer suffered from well-documented firmware instability that led to sudden, unrecoverable failures, and eventually contributed to that company's collapse. And a handful of specific NVMe models in recent years have developed reputations in enthusiast communities for sudden, total failures that leave the drive completely undetected by the system. No slow decline, no warning, just gone. None of this means SSDs are secretly terrible. Modern drives, on the whole, are dramatically more reliable than the ones from a decade ago, with better wear leveling, deeper over-provisioning, and controllers that catch and correct far more errors before they ever reach your files. But more reliable on average is not the same as immune to failure, and that distinction is exactly where people get caught off guard. It's worth addressing the arguments you'll hear that make this all sound like a non-issue. Modern controllers are smarter, true, but a smarter controller manages degradation better. It doesn't stop NAND cells from having a finite number of write cycles. QLC NAND today still tops out around 1,000 cycles regardless of how clever the firmware around it is. Manufacturers test extensively before release, also true, but lab testing happens under clean, stable, controlled conditions. Real-world use involves power interruptions, temperature swings, and firmware edge cases that simply don't show up in a validation lab, which is exactly how drives that pass every pre-release test still fail in the field. My health indicator says 95%. That number is a projection based on ideal conditions, not a guarantee. Controllers can hide degradation extremely well right up until reserved spare space runs out, at which point failure can be sudden rather than gradual. Enterprise drives are safer. Generally true, since they use higher endurance NAND and more aggressive over-provisioning, but they cost several times more than consumer drives and still eventually fail. They shift the odds, they don't eliminate them. And cloud backup covers me? Sync is not backup. If a file gets deleted or corrupted and that change syncs to the cloud copy is deleted or corrupted too. Real protection needs version history, not just a mirror. The honest math on write endurance is actually reassuring for most people once you look at it properly. A typical modern operating system, even with background telemetry, automatic updates, and cloud sync running, writes somewhere in the range of 10 to 30 gigabytes a day under normal use. On a 500 gigabyte TLC drive, rated for a few hundred terabytes of total writes, that pace alone would take decades to exhaust the drive's rated endurance. The math changes fast, though, if you're doing heavy video editing, running large local databases, or downloading huge game installs regularly. That can push daily writes into the tens or even low hundreds of gigabytes, which shortens the realistic endurance window to a handful of years instead of decades. The point isn't that everyone's drive is about to die. It's that your actual usage pattern matters far more than the sticker on the box, and almost nobody checks it. So here's what actually matters. Not fear, just information you can act on today. Start by looking at your drive's real wear level instead of guessing. On Windows, a free tool like Crystal Disk Info will show you smart data straight from the drive, including total bytes written and wear leveling counts. On Mac or Linux, the smartctl command does the same thing from a terminal. Compare your total bytes written against your drive's rated endurance, usually listed as TBW or terabytes written in the product specs. Most consumer drives fall somewhere between 150 and 600 TBW, depending on capacity. If you're already well past half that number, you know more about your real risk than a glance at a green, healthy status bar will ever tell you. From there, work out your actual write rate. Divide total bytes written by power on hours, multiply by 24, and you'll get a rough daily average. That number lets you estimate, conservatively, how much runway is actually left. And it's worth treating that estimate as a ceiling, not a promise, since firmware issues and manufacturing defects don't show up on a spreadsheet. Backups matter more than any of this, and Cloud Sync alone doesn't count as one. The classic 3-2-1 approach still holds up well. 3 copies of anything that matters on 2 different types of storage, with at least 1 copy stored somewhere physically separate. Use backup software that actually keeps version history, Windows file history, Time Machine on Mac, or dedicated tools like Macrium or Acronis, so a corrupted or ransomware hit file doesn't just overwrite your only backup. And actually test to restore occasionally. A backup nobody has ever verified is a backup you're only guessing works. Check your drive's health on some kind of regular schedule. Monthly is reasonable for most people. Watch specifically for reallocated sectors. Pending sectors, or uncorrectable sectors showing up in smart data. Those are early signs of a drive quietly transitioning into failure mode, well before the headline health percentage drops. If you see them, back up immediately and start planning a replacement rather than waiting to see how bad it gets. Speaking of replacement, plan it proactively instead of reactively. If you're sitting around half of your drive's rated write endurance, start researching a replacement and figuring out your migration plan. Once you cross roughly 70%, it's worth just doing it. Replacing a drive on your own schedule means no scrambling, no panic, and the chance to properly wipe the old one before it's recycled or resold, which also protects whatever personal data was on it. Think about how you're actually using your storage, too. If you're doing heavy video editing or anything with large temporary files and scratched data, consider separating that workload onto its own dedicated drive, rather than hammering your main system drive with constant high-volume writes. Keep bulk archival storage, old photos, finished projects, things you rarely touch, on cheaper high-capacity storage, and reserve your fastest SSD for the operating system and active projects. Temperature matters more than people expect. NAND flash degrades faster at higher sustained temperatures, so a laptop that consistently runs hot, or a desktop SSD buried without airflow, is quietly shortening its own lifespan. A cooling pad, better case airflow, or just relocating a drive away from a heat source can meaningfully help over years of use. Protect against sudden power loss too, especially on desktops. A basic UPS can prevent a mid-write power cut from corrupting data or damaging the drive itself. And getting in the habit of shutting down properly instead of forcing power off matters more than most people realize. Keep firmware updated. Manufacturers regularly release updates that fix real bugs, some of which directly address data corruption or failure issues discovered after release. Checking your drive manufacturer's site every few months and actually reading the release notes takes a few minutes and can catch a fix for exactly the kind of problem this video has been talking about. And maybe the biggest mental shift, treat your SSD as a consumable part with a realistic service life, not a permanent fixture. Most drives under normal consumer use will comfortably last somewhere in the 3 to 7 year range, sometimes longer, sometimes shorter depending on workload. Planning for that up front, budgeting for eventual replacement, keeping backups current as a habit rather than an emergency response, turns an eventual failure from a disaster into a minor inconvenience. Here's the uncomfortable truth underneath all of this. Manufacturers are not going to proactively warn you when your specific drive model starts showing systemic problems. They handle warranty claims one at a time, model by model, until enough pressure builds. From lawsuits, from regulators, from public pattern recognition, to force a wider acknowledgement. That's exactly how it played out with those Seagate drives, with the capacitor plague, with early flash memory. The individual failures always show up quietly, one user at a time, long before anyone officially calls it a pattern. That's not a reason to panic about the SSD in your laptop right now. It's a reason to actually check it, back it up properly, and treat replacement as routine maintenance instead of a crisis you deal with after the fact. The physics of NAND flash isn't going away, and no controller, no matter how clever, changes the fact that every cell has a limited number of writes in it. The only real variable left is whether you find that out from a monitoring tool on a random Tuesday, or from a drive that simply refuses to boot one morning. If you found this video helpful, don't forget to like, subscribe to Nolan Tech, and turn on notifications so you never miss future tech videos. So here's a real question worth sitting with. Have you ever actually checked your drive's smart data? Or are you trusting a health percentage you've never once looked at? Drop your answer in the comments. I want to know how many of us have genuinely never checked,